Well, hello there. Welcome to Fluids. This is Ron. We're going to do a little fluid statics today. Fluid statics is basically has to do with stationary fluids. And there are a variety of different principles. Capillary action is one, manometers another. But really, the most important is pressure-fluid height relationship. Got another video coming up on that in the future. But what it comes down to is that if you have a fluid, the first important thing to know is that the pressure at any depth is the same. So if you're 10 feet below, doesn't matter where you are 10 feet below, the pressure is going to be the same, whatever it is, 10 feet below. So one of the fun things that I used to draw when I was working in the Navy is ask this question. So you got all these different tanks, different shapes, different sizes, and where is the pressure greater, at point A, point B, or point C? And the answer is, well, the pressure in any fluid is the same at any depth. It doesn't matter what the shape of the container is. In fact, if the pressure at these 2 points were different, there would actually be motion. There would actually be flow. If the pressure at A and the pressure at B were different, there would actually be flow. So that's the first important point, is that the pressure at any depth in a fluid is the same, regardless of the shape of the container. All right, so what is that pressure? Well, imagine that I've got some tank, and let's let this tank have a certain volume, and the fluid in it is going to have a certain specific weight. Now, specific weight is a thing we use in fluids. It's equal to density times gravity, and the specific weight of water is 62.4 pounds per cubic foot. 62.4 pounds per cubic foot. Well, so then I would ask, what's the weight of the water in this tank? Well, I would argue that the weight is equal to the volume times the specific weight. Let's see how the units work. Volume has units of feet cubed. Specific weight has units of pounds of force per foot cubed. So the weight would be pounds. So the weight of water in this tank would be some number of pounds. Well, now let's say that the tank has some area. What happens if we take the weight and divide it by the area? That would be force divided by area. That is the definition of pressure. It would be pounds force divided by square feet or square inches or whatever. So that's interesting here, that the weight of the water in a tank divided by the area of the tank is the pressure. One more step here. If weight is gamma times volume and area is area, what is volume divided by area? Well, let's let this have some height z. Wouldn't the area times the height be equal to the volume? Yeah. So pressure equals gamma z. And that's really the pressure-fluid height relationship, is that the pressure due to the weight of a fluid is equal to the specific weight of the fluid times the depth. Notice this has nothing to do with the shape of the container. It's just a depth. So that's point number 2. point number 1, the pressure is the same everywhere at a given depth. Point number 2, that pressure is equal to gamma z. Let's make one more point here. You're going to hear about something called Pascal's principle. Pascal's principle basically says that a pressure applied to the surface of a fluid is felt everywhere throughout the fluid. So let's come back to our tank. And we have a pressure applied at the surface of this fluid. That is atmospheric pressure. And it is felt everywhere throughout the fluid and to the walls of the container. So if we wanted to say, well, what is the pressure at some depth, Z? Well, by Pascal's pressure, it's going to be the pressure applied to the surface, which in this case is atmospheric, plus the pressure due to the weight of the fluid, gamma Z. And so this is really the pressure-fluid height relationship. The pressure at any depth is the pressure above, the pressure at any point above, so atmospheric up there, plus gamma Z. In fact, we can make this even more general for those cases where the atmosphere isn't acting. The pressure at any depth is the pressure, I'm going to say above, any point above, plus gamma Z, where Z is the distance from wherever above to that point, to the depth. There's the pressure-fluid height relationship. All right, well, one important thing to note here before I move on, remember with all of these videos that you should be taking notes, and I anticipate that there are questions. So after you've watched a video and we get together again in class, I'm anticipating that you have questions based on the things that we talked about. All right, that's it for fluid statics.